In this section, we are going to discuss message passing as the inter-process communication method. So we, of course, have already discussed shared memory as an inter-process communication methodology. What happens with message passing is that we do not have to resort to shared variables. That's really the key distinction here. So as you may recall, of course, with shared memory, we set up a shared memory region between two given processes, and then furthermore, these two processes can effectively have access to this shared memory region where one process can write to the shared memory region, possibly even read from it, and the other process reads from it. So the producer-consumer paradigm gets nicely fulfilled with the shared memory methodology. What we do with message passing is try to solve the same problem with inter-process communications, but in this instance, what we're doing is we're not sharing variables, we're not sharing a memory region. Of course, from an infrastructure perspective, we may choose to set it up that way, but that we'll get into in just a moment. But instead, what we do is we try to have these two processes communicate with each other as opposed to sharing a memory region and dipping into it. So there are at least two operations when it comes to message passing that need to be implemented as primitives in such situations. And these would be the send message and receive message operations. Pretty easy. And the size of the message itself can be either fixed or variable. Okay. So if we were to consider two processes, let's call them P and Q, that wish to communicate with each other using this message passing methodology, the first thing that needs to be done is a communications link needs to be established between them. And there are lots of different types of communication links. We'll get into that in a moment. And then the further thing that we know we need to do in such a scenario is we need to exchange these messages via a send-receive paradigm. In terms of implementation, clearly there are lots of details that come into play. How are these links going to be established, right? So are they going to be network links? Are they going to be shared memory regions? What really is going to be the underlying infrastructure for the actual communication links? Can a given link be associated with more than two processes? You know, that's something to consider. How many links can there be between every pair of communicating processes? What is the capacity of a given link in terms of, you know, message size and bandwidth? Is the size of a message that can be accommodated by a link, is it fixed or variable? And then finally also, is a link unidirectional or bidirectional? And that in itself is an interesting element that needs to be addressed in the implementation. So let's look at the implementation of a communications link with regard to message passing. At a physical level, these can be shared memory, interestingly, right? So this is a different use of shared memory. They can be a hardware bus implementation. It can be a network, a pretty common way to do message passing used all the time. And then furthermore, at a logical level, the communication link can be direct or indirect. The communication can be synchronous or asynchronous. And finally, there can be automatic or explicit buffering when it comes to these links. The processes when we need to name each other explicitly when we do direct communication. So direct communication is a form of message passing where we are directly addressing each other. Each process is addressing each other by name, by process ID, right? So send P comma message, send a message to process P. Receive Q comma message, receive a message from process Q. As you can see, we are explicitly naming the process here, right? The relevant process to the operation. The properties of the communication link here when it comes to direct communication are as follows. The links are established automatically. A link is associated with exactly one pair of communicating processes. And then furthermore, between each pair, there exists exactly one link. And then finally, again, the link can be unidirectional, but typically is bidirectional. Okay. Now, the problem with direct communication is that it does not scale. We have a hard-coded value that needs to be put into the message every time. I'm going to send to process P. I'm going to receive from process Q. This is hard coding and something that is just not scalable. It is just not a good practice. So another approach that can be taken when it comes to interprocess communication with message passing is to add a layer of indirection. And the way we add this layer of indirection is through a paradigm known as indirect communication, which leverages mailboxes. They're also known as ports. So in this case, messages are directed and received from mailboxes. Each mailbox has a unique ID. The processes can communicate only if they share a mailbox, important to note here. And then with regard to the communications link, there are several properties. The link can be established only if processes share a common mailbox. The link may be associated with many processes. We'll get into that in a moment. Each pair of processes may share several communication links. And then finally, a link may be unidirectional or bidirectional, as by the way was the case with direct communication also. So some operations in the realm of indirect communication would be as follows. You want to go ahead and create a new mailbox. You want to send and receive messages through the mailbox. And then finally, looking again at the life cycle of this mailbox, you want to destroy the mailbox. The primitives, the operations are defined somewhat as follows. You would again have send receive messages, except that in this case, you have send a comma message, right? So send a message to mailbox A and receive a comma message, receive a message from mailbox A. Okay, but definitely as you can see, there's a layer of indirection that's been added here where instead of referring to processes, we're referring to mailboxes. Now, we can have a situation, hypothetically, where you have effectively three processes sharing a mailbox. So here's a mailbox scenario situation where you have processes P1, P2, and P3 sharing mailbox A. Process P1 sends. What happens? P2 and P3 receive, but who really gets the message, right? So who's the final recipient of this message? And the solutions here would be the following. One of those can be valid solutions. One is you allow a link to be associated with at most two processes. Well, if that's the case, then automatically you will only have one recipient. Second, you can allow only one process at a time to execute a receive operation. So even though in this scenario we have three processes and one sends, P1 sends, and you have P2 and P3 there, but if you only allow one of these two, P2 or P3, to execute a receive operation, then we've solved the problem of who gets the message. And finally, another solution to this problem is really to allow the system to arbitrarily select the receiver. Not the best way, but nevertheless, it is a valid solution, and the sender simply gets notified who the receiver was, right? So three distinct ways to solve the problem where you have three processes sharing a mailbox and one process sends, and we really want to know which process who finally gets the message, right? Process P2's or P3's mailbox. Okay. Some more details pertaining to indirect communication. So a mailbox itself can be implemented in such a manner that it is owned by a process or by the operating system. When a mailbox is owned by a process, things are more deterministic. The mailbox is part of the address space of the process. When the process terminates, the mailbox disappears. Each mailbox has a unique owner. There's absolutely no ambiguity as to which process should receive a message sent to this mailbox, right? So a lot more deterministic behavior here. On the other hand, when you have a mailbox owned by the operating system, it is not attached to a particular process. Furthermore, the operating system provides a mechanism that allows a process to create a mailbox, to send received messages through the mailbox, and to delete the mailbox. So now let's jump into the next important topic in the realm of message passing and IPC with message passing, which is synchronization. It's a very important topic when it comes to message passing, and one that is fairly easy to understand, right? So message passing can be blocking or non-blocking. When we say a message passing is blocking, we effectively or often use the term synchronous to equate the two terms as synonyms. The process is synchronous, and what we mean by that is the following: when we have a blocking send, the sender is blocked from doing anything else until the message is received. So once I'm executing the send operation to this recipient, until the recipient receives my message, I am blocked. I can't do anything else. Likewise, a blocking receive is effectively the same analog for the receiver, where the receiver is blocked until a message is available. So if I've set myself up into a blocking receive mode, I will keep waiting for the message, and until the message arrives, I can't really do anything else. Non-blocking is considered asynchronous. So again, these are just terms from computer science that you're all likely familiar with. So non-blocking send is a situation where the sender sends the message and it continues on, right? So it sends the message and it can go on and continue. Likewise, when you have a non-blocking receive, the receiver receives the message, and it can be a valid message or a null message. And then finally, there are a few different combinations that are possible with blocking and non-blocking. So if both the send and the receive are blocking, we have a rendezvous point. Okay, so let's look at some sample code. It is super easy. The producer-consumer sample code becomes trivial when we have blocking operations, where effectively you go ahead and send next produced for the producer, and then on the receiver you receive next consumed, and that's it. There's really not much else to be done. This is a blocking scenario. When we look at the next attribute of IPC using message passing, the next element here is buffering. So of course, with message passing, you're putting messages likely into a queue, and the queue is attached to the link, and the queue can be implemented in one of three distinct ways. The first method is what is known as a zero capacity queue, where there are no messages that are queued on the link. So effectively, the sender must wait, the sender must wait for the receiver, right? So we have a rendezvous essentially, right? So there's zero capacity queue, no messages are queued on the link, and the sender has to wait for the receiver. And the second type of queue that we can have, or the buffering we can have, is what is effectively a bounded capacity buffer, right? So there's a finite length of let's say, n messages that are available in this message buffer, and the sender has to wait if the link is full, right? So you queue up n messages. Once you hit n and the receiver has really not started receiving, you have to wait. And then finally, the third type of queue or buffering mechanism is an unbounded capacity, infinite length queue, where the sender never waits, right? It just keeps dumping messages into this unbounded capacity queue, and assumes that they will get through, and really is not impacted if this queue keeps getting backed up, at least from its desire to keep pushing messages into the queue. And that really rounds it out with regard to IPC with message passing techniques.